Suppose we have two quantitative variables that we would like to determine if they are related in some way. The first thing we do is to make what's called a scatter plot, or a plot on your Cartesian coordinate or XY axes, and then look to see if there may be some type of pattern, something that appears to be linear, maybe a curve like a parabola or something, or even a periodic relationship. In simple linear regression, we're really interested just in straight line relationships between two variables. So we're not really interested in curves or periodic patterns, but really straight line patterns. So suppose we look at weight in pounds and tail lengths in inches for a sample of wolves. So here you can see that weight is plotted on the vertical axis and tail length is plotted on the horizontal axis. The blue dots represent each of the observations, and this sort of gives us an idea that there might be an increasing roughly linear trend, so that as tail length gets bigger, weight also increases for this species of wolf. So if we wanted to eyeball what the line might look like, what we might do is draw a line such as this red one in the graph. We'll talk a little bit later about how to come up with the best line that describes what's going on in the data. But for now, we just want to recognize that there does seem to be an increasing linear pattern in the data. Now keep in mind, these are not going to be exact relationships, but rather there's a general trend and then there's variability off of the line. Notice that the y variable, or what we call the response variable, is always going to be plotted on your vertical axis. The x variable, or the predictor variable, is plotted on the horizontal or the side-to-side axis. The predictor is going to be the known value, so we may be able to easily observe it or obtain it more easily, or it may be something that is known, or in an experiment we may be able to set that value. So the predictor is what is known, and then we want to know what the response variable might be if we know what the predictor value is. So the scatter plot we have shows what's called an increasing or a positive linear trend, because tail length and weight of wolves tend to increase together. Now we are not interested in exact relationships. We recognize that variability exists in real-world data, and we're interested in these sorts of patterns and what we can do to explain some of what's going on. For example, the number of houses that sell during a quarter when the interest rate is the same across those quarters. It's not always going to be the same. You're going to sell different numbers of houses. People who are the same height are not always the same weight. Children who are the same age are not always the same height. And then wolves with the same tail lengths can also differ in weight. So we recognize that there is natural variability in our models. The correlation coefficient, which is denoted by the letter R, is one way to measure what we call the strength of a linear relationship between two quantitative variables, x and y. Some of the things you want to know about the correlation is that R, the way it's calculated, is always between -1 and +1. Okay, it can't be less than -1 and it can't be greater than +1, and typically it is a decimal number. The sign of R, whether it's positive or negative, agrees with the trend in the scatter plot. So if y tends to increase as x increases, then R is going to be positive. But if y tends to decrease as x increases, then R is negative. If R is near 0, then x and y don't tend to increase or decrease together really. They seem to be almost like dropping salt above a table and it just hitting and randomly scattering, and there's no real clear pattern. The two extremes for R positive 1 and negative 1. If r is positive 1, the points have a increasing trend, so you'd have a positive slope in the line, and all those points lie exactly on one line. They form a perfect straight line. If r is negative 1, the points form a perfect line, but now it has a downward trend or negative slope to it. And we'll look at some examples of these. So in this example, these were just points that were on a straight line, and I believe it was just 2 times x plus 1, right? So 2 times 2 is 4, 4 plus 1 is 5. So this lower left point here would be at 0.25, and then 4, if you double it, is 8, and 1 more is 9. Okay, so that goes across to about 9. And all of those points were calculated in that way. So these points actually, if you put a ruler down, would be exactly on a straight line, and you can see that r is positive 1 in this case. Notice if we draw, if you want to call them crosshairs or whatever, these are sort of x bar and y bar values that give us the horizontal and vertical lines to make the 4 quadrants or the 4 regions of the graph. When r is close to positive 1, you're going to see lots of points in the lower left and upper right corner with little to no points in the off diagonals here. So you can see a clear positive trend, and since they're collinear, they're all on one line, then you get r of positive 1 in this example. Now here's one where the points are all in the upper left and lower right quadrants with none in the other. So this looks like there's a clear decreasing linear trend, but the points are not collinear because r is not negative 1. They look like they might be, but if you actually had a ruler and didn't have a big dot but a small dot, then you wouldn't be able to draw one line through all of those points. But it is very close to linear with a negative trend, so what's happening is r is near negative 1 at negative 0.997. And here's just sort of a random scattering of points, so it doesn't seem like if x gets bigger, so as we move to the right in the picture, we can't say, oh, y tends to be getting bigger or y tends to be getting smaller. It's just sort of random all over the place. So this is where r would be near 0 because there's no linear pattern that we can discern between x and y. And here's a situation where you can see there's an increasing linear pattern of some sort in the data, but the points scatter away from the line, so r is near about 0.56 when you calculate this out for this data set. And what happens here is there's an increasing trend, so r is positive. You can see it, so it needs to be probably closer to 1 than 0, but there's a lot of scattering off of where that line might be going through the center of the data. So as a result, it's not going to be real close to 1, and in this case it turns out that it is close to about 0.56, and that is positive because there's an increasing or a positive slope for the data. So going back to our data with the wolves, I put in the sort of x bar and y bar lines for the data. In this case, what would you guess for the value of r? Okay, so you've got some points down here in the lower left quadrant. You got some in the lower right one also. Several in the upper right one. Only one in the upper left one. Okay, so I think you can see that there's an increasing trend of some sort in the data. So I expect it to be positive. The points are pretty far away from where that line might be drawn, so I don't think it'll be real close to positive 1, but I think there's a clear positive linear pattern. So, you know, if you were guessing, you might guess, you know, positive 0.6 or something. And it's not important to be able to guess other than maybe matching which graph goes best with values of R very close to 1, at about a half, near 0, negative zero point 0.6 and negative 0.99 or something. So it would be pretty obvious what the answers would be if you were trying to match graphs up. It turns out that in this case the correlation is calculated to be 0.692 for this data. So you can see that there's a clear increasing linear pattern in the data, and the correlation actually turns out to be 0.692 for this data set.